Hi all, good evening. Welcome everybody to our Python Milano meetup. So just a couple of slides to introduce ourselves and explain to you what we do, basically. So we are Python Milano, a community of developers and hobbyists having fun with Python. What we do? So we do two monthly meetups. There is this one, Python Milano, which is a little bit more generic, let's say. It's in the trail of the Python Software Foundation kind of talk to explain better, if you know what I'm talking about. And we have another meetup for specific for data, which is PyData Milano. And we do a podcast, which is called Intervista Pythonista. Sometimes we hang out and just have a beer together. So everything is on Meetup. So if you want to get a beer with us, now you know where to look at. And also this year in March, we organized a Python conference, Pi for AI. And I think that we are in a good position also to organize another, the second release, let's say, the second version of this conference in April. Okay, this is our main page, milano.python.it. Okay, we want to thank you, our host. We usually change a lot of venues, let's say. We had to add the Weant here because it's not yet. And thank you, Weant, for having us because this place is fantastic. And we want also to thank Python Italia that provided us with the stickers. And I have some in my backpack over there, so you can have one later. And also the microphone for our podcast. And we want to thank you, Alessandro Re and Division Lab that basically provided us all the stuff for the streaming and also the expertise to put in place the streaming also on YouTube. And okay, on the 19th of November, there will be a new PyData Milano meetup. So just subscribe on Meetup and meetup.com and see you there. And now, a dear friend of mine, Nicola. Nicola has a fantastic story to tell us about stars and automation in Python, especially I would say that it's something like IoT the hard way, let's say. And okay, I think I speak enough and I will leave you the mic. You have already one, so you can start. A big applause for Nicola.
So tonight we are going to talk about Python and astronomy, and more in particular, unattended astronomy using a remote telescope. Where does it come, this thing? The thing is, I've been always a fond of astronomy and fond of photography. So I just merged them together. And because I'm a software developer myself, I wanted to join software development with astronomy, with photography. So I put all in a boilerplate, everything, and it came out something like this. Let me tell you a little bit about myself, what I do during the daytime. So from 9 to 6, I've been working for a telco communication company for 23 years now. And the last couple of years, I'm working for the digital market sector. What I do mainly is working for test automation and process automation. At the beginning, wasn't using Python. I started working Python since 2007, 2009, more or less. My first lecture about Python, I got it from Cesare, probably, when we were working together in the same company. So this is what I'm doing in my daytime. During the nighttime, because I don't want to sleep, as I said, I'm a fond of astronomy since elementary school, and my father was a fond of astronomy himself. And I conduct research in collaboration with some international societies for research about variable stars and asteroids. If you don't know what variable stars are, we'll come soon to that part as well. And as a matter of fact, as a side thing, I also do some astrophotography, as I said. So I take pictures of not bodies of a planetary system. So normally I don't take pictures of sun, moon, and planets, but I take pictures of stars, galaxies, nebulas, and so on. And this is my website. So before to get into the Python stuff and how I automated my astronomical observatory, it's very important that you before understand the challenges I get in order to have a completely unattended remote session. So regarding variable stars, are stars that, as I say, variable because they vary in brightness with the time. And these studies help astronomers in understanding the evolution of the stars at the very end of their journey, before to explode, basically. And what about asteroids? Asteroids are just big pieces of stones rotating around our solar system, and we need to track them in order to understand the rotation period and the composition, so basically spectrophotography. And another interesting side is the reconstruction in 3D of the shape of the asteroids. This can be done measuring the curves of the light curves of the asteroids with the time. And because the asteroids and the Earth have a different position during the year, you basically have a different light curve depending on which side of the asteroid you're looking at. Putting all the curves all together, you can reconstruct in 3D the shape of the asteroid itself, which is very nice and very rewarding research. And as I said, astrophotography, last but not the least, I take most of the object of the deep sky, what we astrophotographers call deep sky, which is everything but the solar system. Why I do it? Well, because the human eye is intrinsically limited because it's not like a sensor that you can accumulate photons on the sensor. So our sensitivity is very limited. Then there is another issue. We have also a less detailed vision in the low light. Of course, we started with film photography at the beginning of the last century. But now with the digital area, things are coming much better, much better as far as sensitivity is concerned. So just to tell you something story, this is a drawing from the beginning of the century of the galaxy M31, the Great Andromeda Galaxy. And this is an image of mine took 15 years ago. I didn't even use a special camera. It was just a reflex camera, a reflex digital camera by Canon, and it was just attached to my telescope. And you can see that this is far better what they could do at the beginning of last century. So what are the challenges mainly? We need for astrophotography in general, for any research in astronomy, to have less light pollution as possible. So Milano is definitely not the right place for doing astrophotography or photography or astronomy in general. You need to have a clear sky, and when I say clear sky, it means that it has to be really clear. It's not like the weather forecast, they say it is clear, but then you see some haze, or the sky is not very blue. The sky needs to be exactly blue, because it has to be as transparent as possible. And then we need to track the apparent motion of the celestial sphere. The other thing is that for a remote, so in an unattended situation, we need to have a kind of watchdog for controlling the internet connection, the electricity, and the weather itself. So as far as light pollution in Italy, unfortunately, we are not very well in a good position. As you can see, just some parts of Sardinia are blue. The darkest, the better. So you can see the Emiliano area very well because it's a big red spot. And Rome, Naples, and Turin, more or less the same. And the good thing is that, for instance, in my case, my remote astronomical observatory it's in this small dark blue place, which is near Volterra, around the province of Pisa, and between the province of, at the end of province of Pisa and the province of Grosseto. And there is still possible to see the Milky Way with your naked eyes. And also, if you go to the Apennines or the mountains or the Alps, you can still see the Milky Way. What we do for measuring how dark the sky is. We have a device, it's called the SQM, the Sky Quality Meter, which is just an infrared sensor, basically, tuned on the visible wavelength, and it's attached by Ethernet or USB port to the PC. You can ask for the data, and you get the values, and these values are measured with a unity of measurement called magnitude for square arc second, which is the brightness with the smallest part of an angle. The darker, the better, of course. So, as I said before, we need to have a very clear sky. The relative humidity must be under 70%, and the wind under 20 kilometers per hour. And these are all parameters that I need to monitor in real time when I do an astronomical session. This is an example of my weather station. It's by Netatmo, and there's a nice API I can query straight away in order to understand how the weather conditions are going on. This is a page presented by Netatmo itself, but then by the API I get a JSON response, and I can acquire all the data. You can see it in the graphical way. And then I store it in a DB inside my PC. For the weather forecast, normally I rely, as I said, in real time for the Netatmo device. But for the forecasts, I rely on the online available sites. For instance, Open Weather Map, probably you know about it. And they provide not only Open Weather Map, but also other websites provide APIs that I can query as well in order to have the situation for the next night of observation. Sometimes the API is not available because it's you need to pay for it, but I don't want to pay. So I just developed some crawler using Selenium and Python in order to get the data that I want. One thing is having calculation. Astronomical calculation are, very complex by definition. The first thing I need to understand is when the night is starting. As a definition in astronomy, the astronomical nights start when the sun is below 18 degrees under the horizon. And of course, vice versa. When the night is going to end, the sun is going to be upper than 80 degrees below the horizon. For this calculation, I rely on a famous Python module, which is AstroPy. AstroPy is based, of course, on NumPy and SciPy, and is dedicated only for astronomical calculation. Another thing I need to consider is the position of the moon, because the moon is very bright, and if it's the object I want to shoot is close to the moon, I will not be able to image it, because the brightness of the moon will make the sky much brighter. So I will lose a lot of the detail and the photons that are coming from very far object. Another thing is to consider the phase of the moon and the distance of the moon from the object. Also in this case, of course, I'm using the AstroPy module. Earth's rotation. One thing is clear, the Earth rotates. And this is a problem for astronomy, because of course we need to have a way of compensating the rotation of the Earth, or better, the apparent motion of the stars on the sky. Another thing is, because we are talking about imaging very faint objects, this means that the image is not just a fraction of a second like a daylight picture. It's a picture that its exposure lasts 10 or 20 minutes. So in 10 or 20 minutes, the star's position vary very much. And if I don't have a way of compensating this, I would not get pinpoint stars, but just stripes. And this is not, of course, scientifically acceptable. So what do? We have a mechanical device which is called the mount, which compensates for rotation of the Earth. Basically, we have two motors. These are two-stepper motors. Magari. Do you have a mat? Un tappetino per il mouse, ce l'hai? O qualcosa che posso usare? Okay, in the meanwhile, basically here there are two motors. One is going to compensate for the rotation of the Earth, and the other is going the direction north-south, and the other east-west, of course. There are two types of mounts. This type, which is called German equatorial mount, and the other one, instead is a typical called fork mount. As you see, there are two arms like a fork that holds the telescope within. The most common one is this one. These types are used for very big telescope, normally professional telescopes, not amatorial ones. For compensating the rotation of the Earth, the mount and the connection of the mount is not enough. We need to have something that controls exactly that the stars is exactly in the same pixel for 10 or 20 minutes. You can see that mechanical parts, of course, have some errors. So these errors needs to be compensated. These are compensated with a special CCD camera, which is called auto guide. So basically, this is just a normal camera attached with, to the PC with a USB port or Ethernet port. And every second is gonna take an image of the star that you are using, and will check for the difference of position from the previous image to the new image, and will send a correction to the motor of the mount in order to compensate for the error of the motor of itself. And the most frequent you do the compensation, the better it is. The imaging camera, which is the one that you actually use for taking pictures, it's a very dedicated normal camera. I mean, for a starter, you can use even a Canon, as I said. But then when you have you do some research, it's better to use professional cameras, which are monochromatic normally, so there is no Bayer matrix in front of the sensor, and you use dedicated filters for doing color imaging or selecting a special wavelengths in order to do some special research. And it has to be cooled because we need to lower as possible the thermal noise of the sensors. Normally, this is not needed during daylight because, as I said, the exposure is 100th of a second or 1,000th of a second. Instead, here we are talking of images of 10 or 20 minutes or even more. And that means that the heat of the sensor will start to raise up and will burn all the photons that you have collected from the sensor. So we need to cool it and as much as possible.
Otherwise, there is a pink mouse.
Oh, pink mouse can be fine. Let's try.
Okay. Sorry about that.
È acceso. Si è acceso, spento. Ok, thank you. The imaging camera is the auto guide camera can be connected even by USB port or Ethernet port. Environmental sensor. As an unattended session, I need to be considering, as I said, the power, so internet connection, the power connection, and I use a UPS unit in order to have enough power in case of an outage, in order to close the dome of the observatory and put the telescope in a parking position. Normally, these actions takes around 3-4 minutes, and so I dimensioned the UPS unit for around 10 minutes just to be in the safe side. This is what is called the cloud watcher. It does what it says. There is another infrared sensor and checks for the clouds. If there is a cloud coming in, it will start the emergency procedure and will close the observatory. The other device is a dew controller. As I said, we need to stay preferably under 70% of humidity, but in this case, the dew controller is needed for another reason. Because of dew. You know very well that during the evening, the humidity starts to come down, and you will see it in the morning, the grass is always wet. And the problem is that it doesn't get just the grass wet, but also the mirror or the lenses of the telescope. So I need to avoid this. And another problem is that if the sensor is working very close to the dew point, the dew temperature point of the sensor, I'm gonna get the sensor frozen. So I will get the Christmas frozen stars in front of the image, which is not nice. All of them are connected by a USB or a serial device. Serial device, if you think it's obsolete, it is not. In astronomy, it's still very much used. Then we have other ancillary equipment. I've got the active optics, which is just a piece of glass that tilts itself like 10 or 20 times per second in order to have even better precision than the auto guide camera I told you before. In this case, I can be more precise, especially when the weather or the mechanics of the mount is not perfect. Another nice piece of equipment is the All Sky Cam, which, as I said, is a 360 degrees camera, which images all the sky at once. So getting an image every 5 minutes, I can see also from remote the condition of the sky myself, if I don't want to trust the cloud watcher, and see what is actually the sky looks like. Another question is, of course, the autofocus. You know, we are very much used about the cameras with the autofocus. The telescope has to have an autofocus itself. There are dedicated electronic focusers that are attached to the focus part of the telescope, and they are controlled by USB port as well. So a lot of USB ports are used for controlling a telescope. So in total, the architecture of the observatory is like this. We got all devices connected by USB or Ethernet to my PC, which is in the observatory, in the dome. Then we got the usual internet cloud, and then I've got my PC at home. And this is the way it normally works. As the software architecture is concerned, we've got, as usual, at the lower level, the physical devices. Here, of course, is just some pictures of them. They are not all, but I'll show you something else later. We've got the physical connections. And at the moment, well, here it says Windows 7, but now I'm using Windows 10 as a device driver layer for all of them. As an upper layer, we've got three possibilities. I've got the ASCOM device driver, I've got straight TCP/IP, or controlling some clients, third-party clients. On the top of it, there is AstroScheduler, which is the Python software I developed to control everything. Basically, AstroScheduler is a system integrator. So it takes devices or straight away or directly connected through another client. The reason why I did it like this, not control it straight away, because it was taking a long time to develop, and I wanted to start to use the observatory as soon as possible. So I decided to use the API allowed by this client in order to control the camera and the focusing by using them. So as I said, there is a software system integrator, and it's written in Python under Windows. The beginning was in Python 2.7, but then I moved to 3.11 1 year ago, I think, something like this. What about it? Okay, I told about ASCOM before, but what is? I don't know if you have been developing sometimes using Windows. Windows has got something called the Common Object Model, which is basically an interface between the physical device and the operating system. The COM objects expose basically all the objects, the physical objects, and all the interfaces needed in order to be connected to all the devices in a device-independent way. From COM object, we got ASCOM, which is the Astronomical Common Object Model, which is basically an initiative in order to have COM objects implemented for monitoring, controlling astronomical devices. And this is the website where I normally get all the releases from ASCOM. They've got a very nice API. You just use it as a common object model, and you can do everything you want using Python. And now let's see how. I don't know if you've been always using the COM object with Windows in Python, but basically I need to import the Win32 com.client yes, as a module in my software. And then if I want, for instance, to instantiate the mount, the control of the telescope, I just use the module, the method dispatch, com.dispatch, and I put the string of the name of the type of telescope I want to control, and I get a COM object to work with. They've got properties, of course. They can be read-write or read-only. For instance, I can get the coordinates of the telescope with the telescope.writeAscension, which is the coordinate, one of the two coordinates I was talking about before. And then, for instance, if I want to connect physically actually connect to the device, telescopio.connected equal true, I get the real connection to the device. If I want, for instance, to expose for 30 seconds with the filter number 1, I will do something like camera.expose and the parameters. The 40, of course, is the number of seconds of exposure. There is a not even this one is working fine. So basically, there is a kind of, let's say, issue with using multi-threading in Python with the COM objects of Windows. Because the way it's done, there can be only one COM object per device. And if you want to pass the COM object of the telescope, for instance, to a thread, you cannot just do it straight away, launching the thread and passing the COM object as argument, unfortunately. There is some trick which is presented as a solution. You need to create a kind of object which is called a Marshall object that acts as a bridge between the main thread and the thread that needs to use the object itself. Just in this way, you can pack, let's say, the original object in the main thread, put it inside this bridge object, and send it to the thread. Then the thread will unpack this object and will be able to use the COM object coming from the main thread. Okay. For doing this, just giving you a little bit of detail, you need to import the Python COM module. You need to instantiate with the co-initialize method the Marshall object, which I am calling the vector here. Then I have to call this fantastic long method in order to say, okay, montatura, which is my main thread's object, needs to be marshaled and sent to another thread. So only after I do this, execute this method, then I can go into the object and with a com.dispatch, which is similar to the com.dispatch that we used before to instantiate the object in the main thread, I can get the same object inside the thread where I want to use it. At the end of using the thread, I need to uninitialize the marshalling of the object. So the AstroScheduler, as you see, has a very, very bare-bone user interface. It does what it needs. There are no bells and whistles. Is written in WX Python and for Windows. And the purpose is to control all the activities that the telescope and all the ancillary equipment is doing at that time. So I've got just a very giant log screen, a command line here in the very bottom, and some basic commands, some very basic buttons on the top, which need to open, for instance, I can open a script file. I have a play button, a stop button, and the next four icons, I hope on the bottom you can see them. The next four buttons are for basically opening, closing, and rotating the dome. And the last three one instead for enlarging and reducing the image on display for the screen. How does it work? Basically, I send, interesting. Okay, not my fault. Let me see if I go back and forward. Okay. AstroScheduler works like this. I have a script file, which is basically a sequence of meta commands I developed for controlling all the devices. I send this script file to AstroScheduler, and it will execute it one line at a time. And if there finds some issues, it will try to recover or stop the execution of the session at once. Better be safe than sorry. So, asynchronous events. Because I need to do some, asynchronous programming, and at that time there was no async I/O. What I found out is that I could use the PubSub module. I don't know if you have worked with PubSub. It's called publish, subscribe, also pattern. So basically, there are objects that subscribe to one or more topics, and when one other part of the program sends a message with the topic, special topic, if another part of the module has subscribed to this topic, can get the message and work consequently. PubSub was originally developed for WX Python in order to not have the famous freezing user interface when there is a very long running task. And it works pretty well. Maybe in the future I will use async I/O, but at the moment I don't feel a need of changing. As we say, if it works, don't touch it. And so basically, it works like this. You import the PubSub module. When you want to subscribe to a message, you put subscribe, you put the name of the callback you want to execute when the message arrives, and the name of the topic you want to connect, for instance, astrodome.connect. To send instead the message, I have the method sendMessage, where I put the name of the topic and a sequence of parameters that I want to send together with the message itself. In this case, for instance, a message that goes to the log subsystem. A very bad one. As I said, the scripting language is done just a simple plain text file. So I can write it everywhere, even on the mobile phone. And it could just a sequence, as I said, a sequence of operations, and it stops when there are some failures or interruption. Or if there is a B plan, it will execute the B plan. And this is an example of the scripting language. The at, it means that it has to wait for that time. So at that date, at that hour, it will start to launch and run the script, one line at a time. So basically, mount on, it means connect to the mount. This is the focuser, focus max on. This is the third-party client that connects to the CCD camera, the imaging camera. And here I say, for instance, that mount track on, it means that the mount starts to compensate for the rotation of the Earth. And then, and so on. For instance, here I say, go to this star with these coordinates, with the filter R, which is the red filter, and go and put the telescope on focus. At this time, I can go and say, go to another sequence of coordinates and to these coordinates, and then I start to maybe execute some imaging sessions and so on. At the end of this imaging session, there will be a next one and next one until the end of the session when there is the shutdown command. At the shutdown command, I close everything and I turn off all the devices. So there is, of course, a lot to do with Astroscheduler. The first thing I would like to do is to automatically generate session script. I just specify the object I want to image, and the program, based on the time and of the year, it has to understand automatically if tonight is the right moment to image this object or not, and it will create the sequence by itself. I need to do some more integration of the environmental the weather, because, for instance, one of the things that happens sometimes, it is that some clouds come, so the safety of the observatory will say, okay, the telescope has to shut down everything. So it will close the dome, park the mount, and turn off everything. But sometimes the clouds come and go in 15, 20 minutes. But at the moment, it just stays closed. It will not reopen again. So I need to have more control on the environmental condition in order that if the environmental situation, the weather is coming better and it is stable enough, it should start again the session and starting from where it ended before, in order to better exploit the night, basically. I would like to have the telegram-based commands. So the same command I put in the command line in Astroscheduler, use the telegram for doing this. I already did some tests and it should be working fine with very few line of code. So I think this is going to be done pretty much soon. And then I need to automate more recovery plans for some very corner case conditions. In the long term, instead, I would like to bring Astroscheduler from Windows to Linux. In Linux, they started to build the equivalent of the ASCOM project I told you before, which is called INDI, which is Instrument Neutral Distributed Interface. In this case, it uses XML messages in order to provide the status of each object. This is something that it's very much needed, because I would like to bring back Linux to be working in the observatory. And also because sometimes I have stability issues with Windows. And I would like to thank you for coming here. We have enough time, I guess. Do we have enough time?
How much time you need? I think
I can show you online with the remote session.
Yeah. Would you like it or? Yeah, can go.
If it's working, I hope there is no demo effect.
The deadline is going out at 20.
Okay. So this is the image from the old sky cam of my observatory. As you can see, the sky is not very much clear. There are some very high clouds coming in, but you can still see the Milky Way on the right side. So it's not a very much an excellent night for imaging. As you can see, some other clouds are coming in, very high clouds. So there is a session that started tonight at 6:45, and it's working. You see here, this is the Astroscaler client, which is logging all the instrument in the instructions that is executing. On the right side, on the left side, sorry, this is the auto guide I was telling you about. So there is a star, and I'm correcting 2 times per second the position of the star in order that it stays on the same pixel. This is instead the log of the focusing system, and focusing was quite okay, not the very best of the nights, but it's fine. Here you can see I'm taking 600-second exposure, and now I'm 415 of this image, and I'm imaging with the L filter, which is luminance filters. It means it takes all the light of all the visible spectrum. And this is one of the images it took. Let's see if we can see something. Oh, these are all stars, basically. Okay. Let me see if we can see some objects. It's a very faint object, so you cannot see it straight away. Basically, the light of this object is so faint that in order to get a very good image, I will have to add many images all together in order to reduce the signal to noise ratio. And this is one of the many that is taken. Well, it's working fine, so the demo effect did not happen. And one last thing, this is the Cloud Watcher graph. It says the sky is clear, but not very clear. As you can see, the graph is going a little bit down on the last minutes. And it came up until 7:20, and now it's going a little bit down, probably because of the clouds that we have seen before. And this is pretty much it, but just give you a quick sneak peek of the observatory. This is the internal cam of the observatory. This is my telescope, this is my mount, and this is the slit from where the telescope is working inside the dome. Now it's working with infrared light in order to not disturb the imaging session. In reality, most of the time, when I see that everything is fine, I turn this off because I don't need to watch it, and I even take away the infrared lamp. And of course, from here, I can also hear the audio, so I can hear if there are some strange noises, the dome moving for some strange reason or whatever, people coming in, whatever. And just to show you a little bit around. So this is the pillar where the telescope is. This one is, no, you cannot see the box here is the one that controls the dome, basically. Here is the motor of the dome. And here is the power distribution box that I created for connecting all the devices. Here I've got a panel which is used to take white pictures in white light of the frames. And of course, I can move it in order to check the surroundings. Sometimes there are nice spiders that goes around over the webcam. And that's it. Thank you. Questions? If there are any.
Yeah, we have a first question.
Thank you for the talk. I wanted to ask you two things. Are the sensors powered by the USB itself, or there is an external power supply?
Most of them are powered by themselves, except the imaging camera that needs its own power supply. Of course, the USB switch, it has its own power supply. And that's it. The rest of the things are using the 5 volts of 500 milliampere of the USB 2.0.
Can you control these power switches? Because in my experience, when I worked with USB devices and sensors, sometimes they froze because maybe the data transfer was cache was full or the firmware was unstable. Did you have some problem like rebooting the device or the sensor remotely?
It happened at the beginning with the USB port connected to the dome controller card. But it wasn't an issue with the USB port itself. It was a electrical ground issue that was making interference to the USB.
Okay.
So after I resolved the electricity problem, I solved also the USB problem. And my transfer rate here are very low. So I never have some problem of having probably bandwidth of the USB.
Okay.
So, no cache issues.
Lucky you. The second question was you mentioned different system in order to auto guide and track the position. Is like filtering or smoothing using like camel filtering a thing to help you tracking better the star position, like by software algorithm?
Yes, sometimes with the auto guide, if the sky, sometimes the air of the sky is moving too much, we call it seeing, which is the turbulence of the air mass. When the turbulence of the air mass is very high, then we smooth the imaging of the auto guide a little bit in order to have a better tracking and not following the movement of the air mass.
Okay. Thank you.
Thank you.
Okay. Any other question? Oh, 2 questions here.
Thank you. I have 2 questions. One is, do you use any kind of service to store all the pictures, like S3, or you just download the picture every time you connect to the system?
Okay, normally I keep them in the PC of the dome until I completed the project, and then I compress them and send it to my QNAP hard disk, external hard disk I've got at home.
Okay. And the last question is, how do you connect to internet there? Do you have like a SIM router or how?
Yeah, I've got a 4G router with an external antenna, and it works pretty fine. I've got a very decent bandwidth. It depends also on the time of the day. Maybe in summertime there is more exploiting of the internet bandwidth of that special antenna, but during winter time I don't have much problems. It's quite fast. Sometimes, in the worst of the cases, if I hit a key, maybe I see it after 1 second. But that's the worst of the cases. Normally, it's just working almost exactly like the normal my PC at home.
Okay, thank you.
Yeah, so just one question for me. So you said that your mount allowed you to point the telescope to follow the rotation of the Earth. But if I figure the rotation of the Earth and how the telescope can move, I don't. In my idea, I think that it shouldn't be able to exactly make so that all of the stars are perfectly aligned. So maybe the center ones can be kept aligned, but the mount should move in opposite to the rotation of the Earth, not just pointing like that, but like translating like if it was in the same position as it was before. So is it possible that when you point, only the center stars are actually perfectly aligned, but the ones at the boundaries of your picture just lose alignment because the I don't know, the frustum of of what you're pointing towards just changes, because it's not actually pointing. It's not like it's completely going back to where it was before. You're just adjusting, but not perfectly.
Okay.
I don't know if my question is
I
comprehensible.
understand what you mean. Fortunately, you can see the sky as a rigid sphere.
Okay.
So the same movement here is the same movement I will get here. And because the stepper motors that I'm using are made exactly to make one rotation of the Earth per turn. So you will get exactly the same position.
Okay, but is this just because you're you're doing it for like 20 to 30 minutes? So if you were to do the same thing for 3 hours,
It's
it
the
would
same.
work same. Ah, okay.
It's the same.
Okay, I got it wrong. So thank you.
Any other question? Ooh, wow. What's the first?
I was wondering about, so you mentioned about the focus system, and I was wondering, do you really need focus? So it's just at the maximum? Because we are talking about the very far objects.
Yes, you are correct. The telescope is made to focus to the infinity, and infinity in theory should be always there. But because of difference of temperature, the dilation of the metal of the telescope will make you change the autofocus, the focus position.
Okay. Thank you.
So, thank you for the very nice talk. Just a curiosity and some extra details to his question. You mentioned, if I correctly understood, that you use some smoothing technique to get rid of the wind turbulence of the air, right?
Yeah.
But the tracking system is actually relying on like some PID system, some like a feedback system
Yeah.
that
It's a feedback system.
yeah, so you are following the it is based on the signal for the specific pixel that you are, like, say that the star is positioned on at the very beginning, right?
Exactly.
But it is just done like on just a single pixel, or there is also the possibility that the spot of the light of the star is like on more than one pixel. So in that case, you can, I mean, how do you manage this kind of situation if
Yeah.
can happen actually?
Yeah, for simplicity, I talked about a single pixel. In reality, because we are not on the space, the image of the star is mirrored by the air. So you actually get a blob, not just a single pixel. But you drive exactly on the blob. You've got the algorithm to find the centroid of the star, and you use the centroid of the star to auto guide.
Okay, thank you.
Okay, any other question, curiosity? There was a lot of stuff in that observatory. Wait.
It's just a silly question. How big is the dome?
The dome
Yeah.
is 3.2 meters diameter.
No, just the equipment you show is quite impressive. I think it's just a bit more than a standard like amateur. I think so. If one would like to start, like, what would you recommend to start from, and how much it is the cost that the minimal equipment required to do something like some astronomical
Okay.
picture or
The thing is, prices are astronomical by definition. But if you start with just a tripod and a digital camera, nowadays with these Sony sensors, which are very sensitive and very low noise, you can start to take images of constellations and some parts of the Milky Way in very, very easily. And then you can stack all the images together and take a very good picture. And this is a good beginning. The next step is having something like a mount with a motor that compensates the rotation of the Earth. That's the next step.
otherwise you have to go every night outside Milan, I think.
This is a must.
Of course.
Unfortunately.
Thank you.
I have a question. Are you organizing for the next eclipse in Bilbao next year, or
Well,
a personal question?
I'm not sure about it because it's an eclipse at the sunset.
Yeah.
So it's very difficult that with the weather forecast is good enough to see it on the horizon. Instead, I'm thinking about the other year, which is there is a total solar eclipse in Egypt. So seeing a total eclipse with the pyramids should be nice to see.
Okay. And you will bring your camera and stuff.
Yeah.
And
I hope
photos.
the political conditions will be good to do it.
Okay, nice. Another question.
Thank you for the talk. I'm just curious. What do you do with the data then? So you study yourself. You give them to someone else
Okay.
that study the data.
It depends. For instance, for variable stars, I take the data, I create good graphs, and I send the data to the American Association of Variable Stars Observers, which has a very huge database. And they collect them, and there are then professionals that could pick up the data from the amateur astronomers and then make papers from the data you collected. And you give, of course, you get the credits for the paper, of course. For the asteroids, I'm connected now with an Argentinian group of people that takes a photometry of the asteroids, so curve or rotation of the asteroids, and we are doing some papers as well for an astronomical bulletin magazine. And instead, for the pictures, I do them for my personal pleasure, and I like maybe sometimes to do some exhibition, and I put them on my website.
Thank you.
Okay. Another question? I actually have another question. Any chance to get rid of COM? I mean, and maybe use Linux also instead of Windows?
Yes.
There is something moving, or we are
There is
grounded to
the
Windows?
INDI interface I was telling you about. It's just for that purpose, to be able to use the astronomical equipment in Linux. But the thing is, as you can see, amateur astronomers are very few. The amateur astronomers, which are also software developers, are a few of the few. So the project is going on since almost 10 years, and only now is starting probably to get stable enough to be used. But I didn't feel like moving the step forward because of this. It was still not enough stable for being in production. And you know, if the dome is left open when it's raining, it's a problem there.
Yeah, yeah, I see. And also, I think you prefer to take pictures instead of coding something.
Actually, it's 50-50 because there are times when the weather is very bad. I cannot do anything. So I exploit that time to improve the astroscheduler or doing some modification or bug fixing or whatever.
Okay, great. Any other question? Okay, if there are no other questions, I think we can close here. Thank you, everybody, coming here. Big applause
Grazie.
for- I think it was a great talk, so see you to PyData Meetup in the 19th of November. And I don't remember the place, but Spotify, oh wow, we are going. Okay, so Spotify, it's near Unicredit, I think, in Gallaudet, something like this, so beautiful place. And okay, for the people